In mathematics and computer science, graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. A graph in this context is made up of vertices, or nodes, and lines called edges that connect them. A graph may be undirected, meaning that there is no distinction between the two vertices associated with each edge, or its edges may be directed from one vertex to another. See graph for more detailed definitions and for other variations in the types of graph that are commonly considered. Graphs are one of the prime objects of study in discrete mathematics. Refer to the glossary of graph theory for basic definitions in graph theory. Definitions in graph theory vary. The following are some of the more basic ways of defining graphs and related mathematical structures. Graph, in the most common sense of the term, a graph is an ordered pair G equals a, V, a E, comprising a set V of vertices or nodes together with a set E of edges or lines, which are two-element subsets of V. To avoid ambiguity, this type of graph may be described precisely as undirected and simple. Other senses of graph stem from different conceptions of the edge set. In one more generalized notion, E is a set together with a relation of incidence that associates with each edge two vertices. In another generalized notion, E is a multiset of unordered pairs of vertices. Many authors call this type of object a multigraph or pseudograph. All of these variants and others are described more fully below. The vertices belonging to an edge are called the ends, endpoints, or end vertices of the edge. A vertex may exist in a graph and not belong to an edge. V and E are usually taken to be finite, and many of the well-known results are not true for infinite graphs because many of the arguments fail in the infinite case. The order of the graph is: a graph size is the number of edges. The degree of a vertex is the number of edges that connect to it, where an edge that connects to the vertex at both ends is counted twice. For an edge U, AV, graph theorists usually use the somewhat shorter notation of. Applications. Graphs can be used to model many types of relations and processes in physical, biological, social and information systems. Many practical problems can be represented by graphs. In computer science, graphs are used to represent networks of communication, data organization, computational devices, the flow of computation, etc. For instance, the link structure of a website can be represented by a directed graph, in which the vertices represent web pages and directed edges represent links from one page to another. A similar approach can be taken to problems in travel, biology, computer chip design, and many other fields. The development of algorithms to handle graphs is therefore of major interest in computer science. The transformation of graphs is often formalized and represented by graph rewrite systems. Complementary to graph transformation systems focusing on rule-based in-memory manipulation of graphs are graph databases geared towards transaction-safe, persistent storing and querying of graph-structured data. Graph theoretic methods, in various forms, have proven particularly useful in linguistics, since natural language often lends itself well to discrete structure. Traditionally, syntax and compositional semantics follow tree-based structures, whose expressive power lies in the principle of compositionality, modeled in a hierarchical graph. More contemporary approaches such as head-driven phrase structure grammar model the syntax of natural language using typed feature structures, which are directed acyclic graphs. Within lexical semantics, especially as applied to computers, modeling word meaning is easier when a given word is understood in terms of related words. Semantic networks are therefore important in computational linguistics. Still other methods in phonology and morphology are common in the analysis of language as a graph. Indeed, the usefulness of this area of mathematics to linguistics has borne organizations such as text graphs, as well as various net projects, such as WordNet, VerbNet, and others. Graph theory is also used to study molecules in chemistry and physics. In condensed matter physics, the three-dimensional structure of complicated simulated atomic structures can be studied quantitatively by gathering statistics on graph-theoretic properties related to the topology of the atoms. In chemistry, a graph makes a natural model for a molecule, where vertices represent atoms and edges bonds. This approach is especially used in computer processing of molecular structures, ranging from chemical editors to database searching. In statistical physics, graphs can represent local connections between interacting parts of a system, as well as the dynamics of a physical process on such systems. Graphs are also used to represent the microscale channels of porous media, in which the vertices represent the pores and the edges represent the smaller channels connecting the pores. Graph theory is also widely used in sociology as a way, for example, to measure actors' prestige or to explore rumor spreading, notably through the use of social network analysis software. Under the umbrella of social networks are many different types of graphs. Acquaintanceship and friendship graphs describe whether people know each other. Influence graphs model whether certain people can influence the behavior of others. Finally, collaboration graphs model whether two people work together in a particular way, such as acting in a movie together. Likewise, graph theory is useful in biology and conservation efforts where a vertex can represent regions where certain species exist and the edges represent migration paths, or movement between the regions. This information is important when looking at breeding patterns or tracking the spread of disease, parasites or how changes to the movement can affect other species. In mathematics, graphs are useful in geometry and certain parts of topology such as knot theory. Algebraic graph theory has close links with group theory. A graph structure can be extended by assigning a weight to each edge of the graph. Graphs with weights, or weighted graphs, are used to represent structures in which pairwise connections have some numerical values. For example, if a graph represents a road network, the weights could represent the length of each road. History. The paper written by Leonhard Euler on the 7 bridges of car paragraph Kniggsburg and published in 1736 is regarded as the first paper in the history of graph theory. This paper, as well as the one written by van der Monde on the night problem, carried on with the analysis situs initiated by Leibniz. Euler's formula relating the number of edges, vertices, and faces of a convex polyhedron was studied and generalized by Cauchy and Lilia, and is at the origin of topology. More than 1 century after Euler's paper on the bridges of car paragraph Kniggsburg and while listing introduced topology, Cayley was led by the study of particular analytical forms arising from differential calculus to study a particular class of graphs, the trees. This study had many implications in theoretical chemistry. The involved techniques mainly concerned the enumeration of graphs having particular properties. Enumerative graph theory then rose from the results of Cayley and the fundamental results published by Pascal Q-Bliard between 1935 and 1937 and the generalization of these by de Bruij in 1959. Cayley linked his results on trees with the contemporary studies of chemical composition. The fusion of the ideas coming from mathematics with those coming from chemistry is at the origin of a part of the standard terminology of graph theory. In particular, the term graph was introduced by Sylvester in a paper published in 1878 in Nature, where he draws an analogy between quantic invariants and covariants of algebra and molecular diagrams. Every invariant and covariant thus becomes expressible by a graph precisely identical with a Kekula copyright diagram or chemical graph. I give a rule for the geometrical multiplication of graphs, that is for constructing a graph to the product of in or covariants whose separate graphs are given. The first textbook on graph theory was written by Dar copyright Nezkarnik, and published in 1936. Another book by Frank Harary, published in 1969, was considered the world over to be the definitive textbook on the subject, and enabled mathematicians, chemists, electrical engineers and social scientists to talk to each other. Harary donated all of the royalties to fund the Pascal Q-Bliard Prize. One of the most famous and stimulating problems in graph theory is the 4-color problem. Is it true that any map drawn in the plane may have its regions colored with 4 colors, in such a way that any 2 regions having a common border have different colors? This problem was first posed by Francis Guthrie in 1852 and its first written record is in a letter of De Morgan addressed to Hamilton the same year. Many incorrect proofs have been proposed, including those by Cayley, Kempe, and others. The study and the generalization of this problem by Tayet, Heawood, Ramsey and Hadwiger led to the study of the colorings of the graphs embedded on surfaces with arbitrary genus. Tayet's reformulation generated a new class of problems, the factorization problems, particularly studied by Peterson and Koenig. The works of Ramsey on colorations and more specially the results obtained by Tura N in 1941 was at the origin of another branch of graph theory, extremal graph theory. The four-color problem remained unsolved for more than a century. In 1969 Heinrich Heesch published a method for solving the problem using computers. A computer-aided proof produced in 1976 by Kenneth Appel and Wolfgang Haken makes fundamental use of the notion of discharging developed by Heesch. The proof involved checking the properties of 1936 configurations by computer, and was not fully accepted at the time due to its complexity. A simpler proof considering only 633 configurations was given 20 years later by Robertson, Seymour, Sanders and Thomas. The autonomous development of topology from 1860 and 1930 fertilized graph theory back through the works of Jordan, Kuratowski and Whitney. Another important factor of common development of graph theory and topology came from the use of the techniques of modern algebra. The first example of such a use comes from the work of the physicist Gustav Kirchhoff, who published in 1845 his Kirchhoff's circuit laws for calculating the voltage and current in electric circuits. The introduction of probabilistic methods in graph theory, especially in the study of orders and Ra copyright me of the asymptotic probability of graph connectivity, gave rise to yet another branch, known as random graph theory, which has been a fruitful source of graph theoretic results. Drawing graphs. Graphs are represented visually by drawing a dot or circle for every vertex, and drawing an arc between two vertices if they are connected by an edge. If the graph is directed, the direction is indicated by drawing an arrow. A graph drawing should not be confused with the graph itself as there are several ways to structure the graph drawing. All that matters is which vertices are connected to which others by how many edges and not the exact layout. In practice it is often difficult to decide if two drawings represent the same graph. Depending on the problem domain, some layouts may be better suited and easier to understand than others. The pioneering work of W. T. Tutt was very influential in the subject of graph drawing. Among other achievements, he introduced the use of linear algebraic methods to obtain graph drawings. Graph drawing also can be said to encompass problems that deal with the crossing number and its various generalizations. The crossing number of a graph is the minimum number of intersections between edges that a drawing of the graph in the plane must contain. For a planar graph, the crossing number is 0 by definition. Drawings on surfaces other than the plane are also studied. Graph theoretic data structures. There are different ways to store graphs in a computer system. The data structure used depends on both the graph structure and the algorithm used for manipulating the graph. Theoretically, one can distinguish between list and matrix structures, but in concrete applications the best structure is often a combination of both. List structures are often preferred for sparse graphs as they have smaller memory requirements. Matrix structures on the other hand provide faster access for some applications but can consume huge amounts of memory. List structures include the incidence list, an array of pairs of vertices, and the adjacency list, which separately lists the neighbors of each vertex. Much like the incidence list, each vertex has a list of which vertices it is adjacent to. Matrix structures include the incidence matrix, a matrix of zeros and ones whose rows represent vertices and whose columns represent edges, and the adjacency matrix, in which both the rows and columns are indexed by vertices. In both cases a 1 indicates two adjacent objects and a 0 indicates two non-adjacent objects. The Laplacian matrix is a modified form of the adjacency matrix that incorporates information about the degrees of the vertices, and is useful in some calculations such as Kirchhoff's theorem on the number of spanning trees of a graph. The distance matrix, like the adjacency matrix, has both its rows and columns indexed by vertices, but rather than containing a 0 or a 1 in each cell it contains the length of a shortest path between two vertices. Problems in graph theory, enumeration, There is a large literature on graphical enumeration, the problem of counting graphs meeting specified conditions. Some of this work is found in Harari and Palmer. Subgraphs, induced subgraphs, and minors. A common problem, called the subgraph isomorphism problem, is finding a fixed graph as a subgraph in a given graph. One reason to be interested in such a question is that many graph properties are hereditary for subgraphs, which means that a graph has the property if and only if all subgraphs have it too. Unfortunately, finding maximal subgraphs of a certain kind is often an NP-complete problem. Finding the largest complete graph is called the Clique problem. A similar problem is finding induced subgraphs in a given graph. Again, some important graph properties are hereditary with respect to induced subgraphs, which means that a graph has a property if and only if all induced subgraphs also have it. Finding maximal induced subgraphs of a certain kind is also often NP-complete. For example, finding the largest edgeless induced subgraph, or independent set, called the independent set problem. Still another such problem, the minor containment problem, is to find a fixed graph as a minor of a given graph. A minor or subcontraction of a graph is any graph obtained by taking a subgraph and contracting some edges. Many graph properties are hereditary for minors, which means that a graph has a property if and only if all minors have it too. A famous example, a graph is planar if it contains as a minor neither the complete bipartite graph nor the complete graph. Another class of problems has to do with the extent to which various species and generalizations of graphs are determined by their point-deleted subgraphs, for example, the reconstruction conjecture. Graph coloring. Many problems have to do with various ways of coloring graphs, for example, the four-color theorem, the strong perfect graph theorem, the Adesa-Faber-Lover-SZ conjecture, unsolved, the total coloring conjecture, also called Beazard's conjecture, the list coloring conjecture, the Hadwiger conjecture, subsumption and unification. Constraint modeling theories concern families of directed graphs related by a partial order. In these applications, graphs are ordered by specificity, meaning that more constrained graphs are which are more specific and thus contain a greater amount of information are subsumed by those that are more general. Operations between graphs include evaluating the direction of a subsumption relationship between two graphs, if any, and computing graph unification. The unification of two-argument graphs is defined as the most general graph that is consistent with the inputs, if such a graph exists. Efficient unification algorithms are known. For constraint frameworks which are strictly compositional, graph unification is the sufficient satisfiability and combination function. Well-known applications include automatic theorem proving and modeling the elaboration of linguistic structure. Root problems, Hamiltonian path and cycle problems, minimum spanning tree, route inspection problem, 7 bridges of car paragraph Nixberg, shortest path problem, Steiner tree, 3 cottage problem, traveling salesman problem, network flow. There are numerous problems arising especially from applications that have to do with various notions of flows in networks, for example, max flow min-cut theorem, visibility graph problems, museum guard problem, covering problems. Covering problems in graphs are specific instances of subgraph finding problems, and they tend to be closely related to the Clique problem or the independent set problem. Set cover problem, vertex cover problem, decomposition problems. Decomposition, defined as partitioning the edge set of a graph, has a wide variety of question. Often, it is required to decompose a graph into subgraphs isomorphic to a fixed graph. For instance, decomposing a complete graph into Hamiltonian cycles. Other problems specify a family of graphs into which a given graph should be decomposed, for instance, a family of cycles, or decomposing a complete graph Kn into NaAA1 specified trees having, respectively, 1, 2, 3 NaAA1 edges. Some specific decomposition problems that have been studied include, arboricity, a decomposition into as few forests as possible, cycle double cover, a decomposition into a collection of cycles covering each edge exactly twice, edge coloring, a decomposition into as few matchings as possible, Graph factorization, a decomposition of a regular graph into regular subgraphs of given degrees. Graph classes, many problems involve characterizing the members of various classes of graphs. Some examples of such questions are below: enumerating the members of a class, characterizing a class in terms of forbidden substructures, ascertaining relationships among classes, finding efficient algorithms to decide membership in a class, finding representations for members of a class. See also. Notes. References: Berge, Claude, Thar. Copyright Everyday Graphs Aces Applications, Collection Universitaire de Maths. Copyright Matrix 2, Paris, Dunodda. English edition, Wiley 1961. Methuen and Company, New York, 1962. Russian, Moscow 1961. Spanish, Mexico 1962. Romanian, Bucharest 1969. Chinese, Shanghai 1963. Second printing of the 1962 first English edition, Dover, New York, 2001. Biggs, N. Lloyd, E. Wilson, R. Graph Theory, 1736–1936, Oxford University Press. Bondi, J. A. Murty, USR, Graph Theory, Springer, ISBN A978-1-84628-969-9A. Bondi, Reardon, O.M., Mathematical Results on Scale-Free Random Graphs in Handbook of Graphs and Networks, Wiley v.Ch., Weinheim, 1st ed. A. Chartrand, Gary, Introductory Graph Theory, Dover, ISBN A0-486-24775-9A. Gibbons, Alon, Algorithmic Graph Theory, Cambridge University Press. Reuven Cohen, Shlomo Havlin, Complex Networks, Structure, Robustness and Function, Cambridge University Press. Golombek, Martin, Algorithmic Graph Theory and Perfect Graphs, Academic Press. Harary, Frank, Graph Theory, Reading, Massachusetts, Addison Wesley. Harary, Frank. Palmer, Edgar M., Graphical Enumeration, New York, New York, Academic Press. Mahadv, NVR. Peld, Yuri N., Threshold Graphs and Related Topics, North Hollander. Mark Newman, Networks, An Introduction, Oxford University Press. External links, online textbooks, Phase Transitions in Combinatorial Optimization Problems, Section 3, Introduction to Graphs by Hartman and Weigt, Digraphs, Theory Algorithms and Applications 2007 by Jorgen Bang-Jensen and Gregory Gutin, Graph Theory, by Reinhard Diestel, other resources, Graph Theory with Examples, Haswinkel, Michiel, ed., Graph Theory, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Graph Theory Tutorial, a searchable database of small connected graphs, image gallery, graphs, concise, annotated list of graph theory resources for researchers, Roxy Euro. A Graph Theory IDE, The Social Life of Routers, a Euro non-technical paper discussing graphs of people and computers, Graph Theory Software, a Euro tools to teach and learn graph theory, online books, and library resources in your library and in other libraries about graph theory.